Welcome to my 68th tutoring session in advanced chemistry. In this video, I'll explain the UV visible spectroscopy and lambda max of polycyclic aromatic system, carbonyl compounds, benzene derivatives, and other conjugated systems. Polycyclic aromatic compounds are made up of two or more benzene rings that are fused together at ortho positions. And this results in formation of polycyclic aromatic compounds. Now, naphthalene is simplest of the polycyclic aromatic hydrocarbon, where you find the two benzene rings are fused together at the ortho positions. The examples of other polycyclic aromatic hydrocarbons are anthracene, tetracene, pentacene, and hexacene. In case of anthracene, you find three benzene rings fused together at ortho positions in a linear fashion. And in case of tetracene, you find four benzene rings fused together at ortho positions. For pentacene, five benzene rings are fused together at ortho positions, while for hexacene, you find six benzene rings fused together in a rectilinear manner at ortho positions. Now, in benzene ring, you find alternative arrangement of single bond and double bonds in a cyclic manner. You find three double bonds and three single bonds that are in alternative arrangements in a cyclic manner. Each corner of the benzene ring represents one carbon atom that is covalently bonded to a hydrogen atom. Each carbon atom of the benzene ring, it has a p orbital with an odd electron in it, and these p orbitals on adjacent carbon atoms, they undergo sideways or parallel overlapping, and this results in formation of delocalized pi molecular orbital, and there will be delocalization of pi electrons. So whenever there is delocalization of pi electrons, the energy gap between the HOMO and the LUMO, it reduces. And these pi electrons, they are loosely held, while the sigma electrons in the sigma bond, they are tightly held. When the right amount of energy provided by the UV visible radiation, when it impinges or strikes the polycyclic aromatic compound, the loosely held pi electrons, they absorb the energy provided by the UV visible radiation, and they undergo transition from the ground state to the excited state. Now, the pi electrons present in the pi bonding orbital in the ground state, they absorb the energy provided by the UV visible radiation, and they undergo excitation, and this brings about the transition from the ground state to the excited state. Now, the pi electrons present in the pi bonding orbital in the ground state is represented by pi symbol, while the pi electrons in the excited state are represented by pi star, represented in the antibonding orbital. So when the right amount of energy provided by the UV visible radiation, when it strikes or impinges the polycyclic aromatic compound, the loosely held pi electrons undergo transition from the ground state to the excited state. Now, the pi to pi star transitions are observed in compounds with unsaturated centers. like in case of compounds like alkenes, carbonyl compounds, and aromatic system. So wherever you find the unsaturated centers, you can observe this phenomenon of excitation from the ground state to the excited state. That is, you will find the transition from pi to pi star. Now the energy required for bring about transition from the ground state to the excited state in case of naphthalene is represented by delta En. Now when one more ring is added up to the naphthalene ring, it results in formation of anthracene. So in case of anthracene, you find 3 benzene rings fused together at ortho positions. And you can see the energy gap as lowered. And the energy gap in case of anthracene is labeled as delta Ea. So delta Ea is the energy required to bring about transition of pi electrons in anthracene from ground state to the excited state. Now ground state is also called as the highest occupied molecular orbital. The other name for excited state is least unoccupied molecular orbital. That is HOMO and LUMO. And the energy gap is further lower in case of pentacene. So pentacene, you find 3 benzene rings fused together at the ortho positions. While in case of hexacene, you find 6 benzene rings fused together at ortho positions. So as the number of benzene rings add up, you find linear arrangement of this benzene rings, and there is increase in conjugation. So each benzene ring, remember, there are 3 double bonds that are in conjugation with each other. So as the number of benzene rings add up, there is increase in conjugation. You can say there is extended conjugation. So with increase in conjugation, there is increase in delocalization of pi electrons. And this lowers the energy gap between the ground state and the the excited state. So in case of benzene and naphthalene, very high energy is required to bring about the transition from the ground state to the excited state. Now the wavelength of the ultraviolet region, it ranges from 200 to 380 nanometers. So the transition of pi electrons from the ground state to excited state in case of benzene and naphthalene needs higher energy, and therefore absorption occurs in the UV region. While polycyclic aromatic compounds like anthracene, tetracene, pentacene, and hexacene, they exhibit extended conjugation. So there is increased conjugation or there is extended conjugation in case of anthracene, tetracene, pentacene, and hexacene. And as a result of extended conjugation or increase in conjugation, there is increase in delocalization of pi electrons, and this lowers the energy gap between the ground state and the excited state. And as the energy gap between the ground state and excited state is lowered, and therefore these compounds, they absorb in the low energy visible region. Now the wavelength of the visible region ranges from 380 to 800 nanometers. And therefore these compounds with extended conjugation, they absorb in the visible region. And the visible region, the wavelength is more as compared to the UV region. Now wavelength is the distance between two successive maxima and minima. So wavelength is more in case of visible region, while wavelength is less in case of the high energy ultraviolet region. The energy of the electromagnetic radiation is given by the equation E is equal to HF, where E represents the energy of the electromagnetic radiation, h Planck's constant, and f frequency of the electromagnetic radiation. Now frequency is equal to c by lambda, where c represents the velocity of light and lambda the wavelength of the electromagnetic radiation. So energy of electromagnetic radiation can also be represented as h c by lambda. Now in the second equation, you can see that the energy of the electromagnetic radiation is inversely proportional to the wavelength of the radiation. So energy of the electromagnetic radiation is directly proportional to the frequency. That is, with increase in frequency, energy of the radiation increases. And as per the second equation, the energy of the electromagnetic radiation is inversely proportional to the wavelength. That is, with increase in energy, the wavelength decreases. And with increase in wavelength, the energy decreases. So in the visible region, you can find that the wavelength is more. Wavelength is increasing. So as the wavelength increases in the visible region, the energy of the radiation decreases. And therefore, in case of polycyclic aromatic hydrocarbons like anthracene, tetracene, pentacene, and hexacene, because of extended conjugation, it lowers the energy gap, and because of decrease in the energy gap, these compounds they absorb in the visible region. Why? Because in the visible region, it is of low energy, or you can say it is of longer wavelength. So energy and wavelength are inversely proportional. So the decrease in energy, that is delta E, for the promotion of an electron from a pi bonding orbital, that is HOMO, to pi star, that is anti-bonding orbital, LUMO, it occurs due to increase in conjugation. Now let me explain the excitation of pi electrons from the ground state to the excited state, considering ethylene as a representative example. Now ethylene is a simplest of the alkene. Now ethylene is characterized by presence of carbon-carbon double bond. And the carbon-carbon double bond in ethylene, it is constituted by a weak pi bond and a strong sigma bond. Now the pi bond is highlighted in purple color, while the sigma bond is highlighted in yellow color. Now pi bond is formed by sideways or parallel overlapping of p orbitals. Now in a p orbital, there are two lobes, upper lobe and the lower lobe. And the upper lobe and the lower lobe of a p orbital, it is separated by a nodal axis. So the probability of finding the electron is 0 at the nodal axis, or I can say the electron density is 0 around the nodal axis. So this is how the p orbital is formed. Now the p orbital, that is the pi bond. Now pi bond is weaker because it is formed by sideways or parallel overlapping. So what about the sigma bond? Now sigma bond is stronger than the pi bond because it is formed by endwise or linear overlapping of the sp2 orbitals. Or you can say a sigma bond is stronger because it is formed by overlapping of sp2 orbitals along the internuclear axis, that is along the x-axis. That is why it is a stronger bond in comparison to the weaker pi bond. When right amount of energy provided by the U visible radiation, when it strikes or impinges an unsaturated molecule, the pi electrons present in the pi bonding orbital, that is pi bonding molecular orbital, it absorbs the energy given by the U visible radiation and undergoes transition to the excited state. So the electrons, that is pi electrons present in the bonding pi molecular orbital, is represented by symbol pi, while the electrons, that is pi electrons in the excited state in the anti-bonding orbital, is represented by pi star. Now this excitation process of the pi electrons in a unsaturated molecule can also be represented in a different way. So when the right amount of energy provided by the U visible radiation, when it strikes or impinges the unsaturated molecule, pi electrons present in the bonding pi orbital, that is in the ground state, they absorb the energy provided by the radiation and they undergo photo excitation. And this results in excitation of the electron from the bonding pi orbital to the anti-bonding pi star orbital. Now in case of anti-bonding pi molecular orbital, the electron cloud holding the atoms together redistributes itself and the orbitals occupied by the bonding electrons no longer overlap. Now, as can be seen in this diagram, you don't find any overlapping in case of anti-bonding pi molecular orbital, while there is effective overlapping of the pi bonding molecular orbital, that is in the ground state. Now benzene and naphthalene are colorless compounds, while other polycyclic aromatic hydrocarbons like anthracene, tetracene, pentacene and hexacene, they are highly colored. Of these four colored compounds, anthracene is cream or pale yellow colored. It is very light colored because this compound absorbs at a wavelength of around 375 nanometers. So this is the wavelength where the UV region ends and the visible region begins. And that is why anthracene is very pale colored. While other compounds with more number of benzene rings fused at ortho position in a rectilinear fashion, they absorb at higher wavelengths and hence they are brightly colored. So tetracene is a bright orange colored compound, pentacene is blue colored, and hexacene is a bluish green colored crystal. So these compounds are colored because they absorb in the low energy visible region. And why they absorb in the low energy visible region? Because of the energy gap. So energy gap between the HOMO and the LUMO is very low in case of anthracene, tetracene, pentacene and hexacene. Now here's the U visible absorption spectra of tetracene, pentacene and hexacene. And in the first spectra, P1 represents the lambda max of pentacene. So P1 represents the lambda max for pentacene. It is around 680 nanometers. And T1 represents the lambda max for tetracene, which is around 530 nanometers. And when you observe the graph C, you find that the lambda max for hexacene is around 780 nanometers. Now the absorption curve for hexacene is represented by a black curve. So black curve in the graph C. So as the number of fused aromatic ring adds on, as the number of rings increase, the energy gap between the HOMO and the LUMO increases and thereby absorption occurs at a higher wavelength. So benzene lambda max is around 254 nanometers, while lambda max in case of hexacene is around 780 nanometers. So the difference in wavelength is because of conjugation, extended conjugation. So polycyclic aromatic hydrocarbons consist of many orthofused benzene rings in a rectilinear arrangement, where you find extended conjugation. So as the number of condensed rings increase, there is notable enhancement in absorption, shifting the absorption spectrum towards longer wavelengths. That is in visible region. So visible region is a low energy region of longer wavelengths. So hexazine is an aromatic compound consisting of 6 linearly fused benzene rings, and that is why it is colored, because it absorbs in the visible region. Now let me explain the absorption spectra as well as the lambda max of carbonyl compounds. Now acetone is a normal ketone, is a simplest of the ketones. It is a carbonyl compound and is characterized by the presence of a carbonyl group, that is carbon oxygen double bond. While in case of methyl vinyl ketone, it is a conjugated ketone where carbon oxygen double bond is conjugated with carbon carbon double bond. And as I already mentioned, whenever there is conjugation, there is delocalization of pi electrons, and whenever there is delocalization of pi electrons, the energy level of the conjugate system, it decreases, and hence the compound absorbs at longer wavelengths, resulting in greater lambda max values. And in case of methyl oxide, you find that the terminal hydrogen atoms are replaced with 2 methyl groups. And how do you identify an alpha and beta carbon in case of conjugated carbonyl systems? The first carbon with respect to the carbonyl carbon is the alpha carbon, and the second carbon with respect to the carbonyl carbon will be the beta carbon. So assignment of alpha and beta carbons is purely based on considering the functional group. Here it is the carbonyl group that we are considering as a reference. So how do you identify the beta carbon in case of conjugated carbonyl system? So the beta carbon refers to the second carbon in a chain related to the functional group. So here the functional group is the carbonyl group. So it can also be an alkene group. So with the increase in number of double bonds, you can see the lambda max value increases. Acetone, it is 187 nanometers. In case of methyl vinyl ketone, it is 230 nanometers. And with alkylation, in case of methyl oxide, you find additional presence of 2 methyl groups on beta carbon. So with the increase in or addition of alkyl groups, there is further increase in the lambda max. So bathochromic shift or red shift is due to 2 reasons. One is due to conjugation, that is increase in the number of double bonds and that are in conjugation with each other. And second reason is alkylation, that is presence of alkyl groups. So in case of methyl oxide, both the factors are contributing towards the bathochromic shift or the red shift. So there is presence of conjugation as well as presence of alkyl groups. And how to theoretically calculate the lambda max for a conjugate system, that is conjugate carbonyl system. Now let's try and calculate the lambda max for the methyl oxide, which is a conjugate ketone. Now the base value for alpha beta unsaturated ketone is 250 nanometers. So this is as per Woodward-Fieser rules. So as per Woodward-Fieser rule, any conjugate system where you find the presence of alpha beta unsaturated ketone, like in case of methyl oxide, you assign a base value of 250 nanometers. So what is base value? Now base value is nothing but a numerical value assigned to a conjugate system, which is a alpha beta unsaturated ketone. And when you observe the structure of methyl oxide, you find that in addition to the presence of the alpha beta unsaturated ketone system, there are presence of 2 alkyl groups. That is two methyl groups covalently bonded to the beta carbons. So an additional increment value of 12 is given for each methyl group added to the or covalently bonded to the beta carbon. So in case of misteryl oxide, you find two methyl groups covalently bonded to the beta carbon. And therefore, the theoretical lambda max value will be 215 plus 12 plus 12, that is 239 nanometers. 215 because the base value of 215 given for the presence of this alpha beta unsaturated ketone system in misteryl oxide. And why 12 is added twice? Because two methyl groups are covalently bonded to or attached to the beta carbon. So for every alkyl group attached to the beta carbon, you add a or you give a increment value of 12 nanometers. So here you find two methyl groups attached to the beta carbon, and therefore you add 12 nanometers twice, and that is equal to 239 nanometers. So 239 nanometer will be the lambda max theoretical calculation, but the practical observed value is around 250 nanometers. Now sometimes both the theoretical as well as the practical experimental values may be the same, and sometimes it may vary. The values should be very close. So misteryl oxide is a conjugated ketone where the carbon-oxygen double bond is conjugated with carbon-carbon double bond. And there is delocalization of pi electrons due to mesomeric effect. Now mesomeric effect refers to polarity produced in a molecule as a result of interaction between two pi bonds. And the mesomeric effect is represented by a curved arrow where the arrow end represents the mobilization or movement of loosely held pi electrons towards the more electronegative oxygen atom. So there are two driving forces for the delocalization of pi electrons in case of alpha beta unsaturated ketone. First is the greater electronegativity of the carbon atom, which is around 3.5 on the Pauling electronegativity scale. And second is the easy mobilization of the pi electrons as it is loosely held. Now the conjugation, it decreases the energy difference between the HOMO and the LUMO. That is the energy gap between the bonding pi molecular orbital and the anti-bonding pi molecular orbital. Now the pi electrons in the ground state is represented by symbol pi, while the electrons, pi electrons in the excited state is represented by symbol pi star. So pi to pi star transitions are observed in compounds with unsaturated centers like alkenes, carbonyl compounds and aromatics. So I have tried to cover all these three in this video. So delta Ex is the energy required to bring about transition of loosely held pi electrons from the ground state to the excited state in case of acetone. And delta Ey is the energy required to bring about transition of pi electrons from the ground state to the excited state in case of methyl vinyl ketone. And delta Ez is the energy required to bring about transition of pi electrons, loosely held pi electrons from the ground state to the excited state in case of misteryl oxide. And with the extended conjugation, the energy gap will be further reduced. So the lambda max value for a compound depends on the energy difference between the two levels, the ground state and the energy state levels. So the energy difference for acetone is delta Ex, energy difference for methyl vinyl ketone is delta Ey, and energy difference for misteryl oxide is delta Ez. And with extended conjugation, the energy gap will further get reduced. So with increase in conjugation, there is increase in delocalization of pi electrons And with increase in delocalization of pi electrons, it lowers the energy gap between the HOMO and the LUMO, that is the ground state and the excited state. And as an outcome of this event, the absorption of the usable radiation by the molecule occurs at a longer wavelength. And that is how the lambda max of the compounds increase with increased conjugation, because their absorption occurs in the visible region. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.